Thank you very much. Thanks, Anna, and my thanks to the Open Data Science Conference for inviting me to speak. It's a great privilege and an honor to speak to all of you today. So, let's just gawk at this title for a moment. Machine learning and artificial intelligence, the difference between knowledge and action. Very scary, very exciting. Okay, so I'll talk for a moment about diversity of backgrounds. So, like me, I'm sure many of you work with people from a great variety of backgrounds. You talk to 10 data scientists, they came from 12 different places. So as for myself, I work with a bunch of ex-physicists, a bunch of people who are like, man, we ran out of funding, but we got all these math skills. Who will pay us to do this stuff? And I work with 3 separate people who work at CERN, or used to work at CERN, which is a famous research facility in Switzerland where they discovered the Higgs boson. And in fact, this caused one of my coworkers to lean over to me one day and said, "Hey, Don, do you remember the day they tried to ban drinking before noon at CERN?" And then the response to that was people brought thermoses into work filled with booze. And I said, "No, I don't remember that day because I didn't work at CERN, because I'm not a physicist." So my background, at least where I work, it seems to be somewhat unusual in that I came from computer science and artificial intelligence, and I think that gives me a little bit of a unique perspective, and I just wanted to share a little bit of that with you today. So let's look at a couple of examples of intelligent systems. So forecasting, we're not allowed to use the word prediction, right? Because that's fraught with liability. We say forecasting. So forecasting. This is a really cool example of Airbnb looking at historical data in order to tell you how much money you should charge in order to charge for rent, or to maximize your expected revenue. Cool application. Recommender systems, right? Everyone knows this example. Netflix, it's a triumph of database approaches to solving a problem. Everybody knows what this is all about, but essentially using simple knowledge like what queries people typed in, and like little manually created attributes of movies, like does this movie take place at college, or like does it feature a protagonist with red hair, or things like this. And just from little things like this, you create like immensely great recommendation systems that have really made Netflix powerful. So I actually know the dude who wrote it, Sadiq Kapadia over there, and he tells me that even to this day, every recommendation call passes through a desktop machine that sits on his desk. And I said, "I kind of don't believe you, Sadiq. That's a lot of calls." And he's like, "It's so efficient. It's that efficient. Every single call goes to that one machine." He's a cool dude. He's very intense. Anyway, so these are all super amazing accomplishments, right? They're all applications of machine learning, and if we saw any machine do this, we would all agree that it takes intelligence to do these things. And so it is very reasonable to ask, is that what there is in building intelligent systems? Is that what the game is all about? So to answer that question, let's look at a couple of additional examples. So NASA. NASA is one of the foremost practitioners of artificial intelligence out there, period. This is by necessity, really. So like, for example, if you look at the Mars rovers that are crawling all over the face of Mars right now, it takes 15 minutes for a signal of light to travel from here to there. So manual control is really just not feasible. They must make decisions autonomously. So this particular example is about autonomous satellites. So satellites that are in orbit of various things, like asteroids, planets. And what they do is they give it very high-level commands. They say, like, I want you to go to this series of asteroids and get good pictures, quote-unquote, good pictures, whatever that means, up to the satellite to determine. So it takes these high-level goals and it translates that into base action. So things like, fire this thruster at this intensity for this duration of time. Move your camera orientation here, change your own orientation to this thing. It takes this very vague task, take this image, and turns it into a sequence of basic actions. Simple example. Crate stacking. So imagine this is just a robot arm. We're looking at an initial state of the world, just a bunch of disordered blocks. We would like for it to look like what it looks like on the right side. As human beings, we look at this, we immediately know what to do, right? We would like for a robot to be able to look at this and just know what the answer is. So there are applications of this, for example, in warehouses. There are robots all over warehouses that in fact do crate reordering and stacking. So what I'm trying to get across is that however you solve the previous problems, whatever method that you use, there are requirements, right? You have to reason about what is the impact of what I am doing on an environment. I'm changing the environment. And secondly, I have to reason about organizing a sequence of actions to affect a long-term goal. One more example. I love this example. So let's suppose I have a bunch of logical statements, just a bunch of premises. Is it possible to just automatically conclude what are all the things which are necessarily true given these premises? So these are called theorem-proving systems. So this is an example of a page from Chapter 2 of Principia Mathematica, written by Whitehead and Russell. And it turns out that a theorem-proving system was able to reproduce all of the theorems in Chapter 2, and in many cases produced shorter proofs than the authors were able to produce. So what I'm trying to express is that machine learning is focused on learning from example, making generalities from example, and then applying those to future situations. AI is sort of more broadly concerned with action, organizing action to achieve a long-term goal, and everything that is contained within that problem. So what I want to talk about today is how we think about machines reasoning about action. How does this relate to machine learning? How do these two fields work together to build intelligent systems? And they certainly do. And why you should care. Okay, let's go back to this example of the robot arm. So we look at this thing, we would like the robot to look at the state on the left and just know what to do, to turn it into the thing on the right. And so an approach to this problem is to say, oh great robot, here is everything you are capable of doing. Here's a list of actions that are available to you. And an example of one of those actions, we write them as an operator. So, description of the action, unstack box A from box B. In order to do this action, the preconditions have to be true. So, there has to be nothing on A, it has to be clear. The arm has to be not holding on to anything, and A has to be on top of B. After I do this action, everything in the effect row is going to happen. So, A is going to not be clear, the arm will not be empty, it's going to be holding something, and A will no longer be on B. And so this is a very simple domain, right? You could pretty much capture everything you'd want to do in this domain with these four operators. And so this is a plan which would accomplish this problem right here, right? Pick up blue, put down blue, pick up red, put red on top of green, pick up blue, put blue on top of red. So how do we arrive at these plans? So an initial proposal is search-oriented method. So what you do is you think about what is every possible thing I might do first, right? After doing each one of these proposed actions, the world is going to be in some resultant state, some hypothetical future. For each one of those futures, let's then reason what's every possible thing we might do second. And then you continue doing this, and eventually you arrive at a state of the world in which all of the goals you're interested in are accomplished. And you follow the path from the root to that leaf node, and you have a plan that takes you from the initial state to the goal state. There's a problem though, right? I mean, as you can imagine, as you sort of examine any kind of remotely realistic domain, it becomes intractably difficult, right? So it turns out that the time complexity for uninformed planning is exponential in the number of steps of your plan, and the branching factor is the size of your action space. And actually applying these to real systems, all of them use machine learning-based approaches to intelligently narrow which part of the search space you're looking at. So you intelligently decide which branches of this tree I'm going to search through. So can anybody think of such an application? Off the top of your heads. Silence. Okay. This is an example. So this is Deep Blue playing Gary Kasparov. This was a rematch, actually. And so this is precisely what Deep Blue does in order to solve this problem. It uses search-based approaches that are informed. in order to look through the precisely best parts of the search space. So today, you can get lots of really great off-the-shelf planners that do all of the above, that make plans that are thousands of steps long, and it does it in seconds or less. These are great open source, free solutions. The fast forward planner in particular is really, really good. And that is planning. So I wanted to talk about a couple of applications of this. Let's skip that one. So military planning, by which I mean military logistics planning. So this is a really interesting example. So think, I've got a military base A, it's got a bunch of stuff in it, and I want to move it to base B. So back in the day, the way that people would solve this problem is you would have a person who sat and thought long and hard, like thought for months, basically producing a plan that was thousands of steps long that says like, all right, I want this crate of oranges to go onto this flatbed truck, and then it has to go onto this boat, and then there has to be someone who receives it here, and then someone who unpacks it here. And this is like a very complex logistical operation that involves synchronizing many, many different resources. It took people months to prepare. So what they did is they engaged researchers at Dartmouth, and they created the DART Logistics Planner. And this planner created an automated solution to this problem, and it did it in hours instead of months. And the resulting money saved in terms of man-hours was so much that it was more than all of the money DARPA had awarded to AI research in the preceding 30 years combined. So the military was totally sold. AI research is awesome. Let's do more of that. Okay, so I know what you're thinking. This is not AI, it's just search, right? And that sentiment actually has happened several times where like there's sort of a task where we sort of agree like, all right, it takes intelligence to do this thing. And then when we make some progress on solving this problem, people are like, it's not really AI. And this led Larry Tussler from Xerox PARC to come up with the sentiment, AI is whatever hasn't been done yet, because once it's been done, that's not really AI. And this sort of gets to this dichotomy between strong and weak AI. So weak AI says like, just like whatever means necessary, get the thing done. Strong AI says, we care how it is done. You have to find the solution in a way that is similar to how a human being would find the solution. So this is really cool. We're able to, these systems have been used to solve like super complex problems, but there are big problems with it, right? So one of the big assumptions that it has is that the world is deterministic, meaning that I know exactly what's going on in the world and I know precisely what the impact of performing an action is going to be. And anyone who has any experience working with real robots knows that this is extremely not the case. For example, if I give my robot hand the command, I want you to grasp this apple. Well, sometimes that happens. And sometimes it doesn't. Sometimes it fails. Maybe more often than not it fails. Another assumption is that the world is fully observable. So this is definitely not true when you have teams of robots or of agents working together where in order for me to make a decision, I have to know what you are aware of. So for one Mars rover to do something, I have to know what another Mars rover has access to. And the question is, what are you going to do about it? How do we decide what to do in the face of this? And lastly, we're making the assumption that a goal is specifiable and reachable, which is definitely not always true. Sometimes a goal is just some vague trend you want to make happen. So the answer to this is something called decision theory. And this is really where every single technique that is in machine learning and database approaches really, really comes to bear. And decision theory is really where every modern intelligence system uses in order to work today. So I'm going to talk about each of these things in turn. So probability, what does probability get us? So this is an example which sort of gets into what I do for my regular job, which is essentially AI applied to systems and infrastructure. So let's think about the following situation. I got some server, and I've got a client. The server has a video on it, and the client is trying to stream that video. So like the simplest version of a Netflix service. And in between is a server gateway and a client gateway. Now let's suppose at the client end, the client observes that the video is slow. Right, it's just a simple observation. And there might be like 10 million things that are responsible for this, right? Like there could be a DNS entry that's misconfigured, something could be on fire, God knows what happened. could be one of a million things, but all we have is this one observation. And so how do we find the most likely explanation? So let's consider two possible explanations. Server-side congestion and client congestion. Server congestion means the server is just inundated with requests, and so the client can't get the data that it needs. Client congestion means like the client is running the customer is running like a BitTorrent server at home, and because of that, like they can't get, there's too much contention for video data. And so the way that you would phrase this question in like a Bayesian statistics format is you would say, what's the probability that server congestion is to blame, given this observation that the client is slow, versus what's the probability that client congestion is to blame. So let's consider evaluating one of those statements. So the probability that the client congestion is to blame, given this observation. So the Bayesian statistics answer to this, right, is you look at, essentially, what is every possible configuration of the system where my observation is true, where client congestion was in fact to blame. Essentially, what are all of the ways in which client congestion is to blame? And are those ways more than the number of ways in which server congestion could possibly have been to blame, given this observation? And in this case, maybe that's true. So given that the client is slow, maybe there are just more ways for client congestion to be responsible. And so that's what we go with. But now, let's suppose that another client comes in, has exactly the same complaint. So someone, totally different house, says, I'm trying to examine the same video file, but now it is slow. And you can sort of intuitively get this idea that as more and more customers are complaining about video, there being a problem with video, that slowly the blame should shift from the client to the server. And you can express this with probability. So if you try to perform the very same comparison now, the probability that server congestion is to blame given these two observations versus client congestion, and you try to evaluate the same expression, now you're saying, I want to find out what are all of the ways in which client congestion might be to blame that are consistent with these two observations that I've seen. And you might find that now there are fewer possible ways for that to occur when compared with server congestion. And so maybe it wouldn't occur with two clients, this would be born out of your data, but as the number of clients that are repeatedly complaining of slow video increases, slowly this inequality starts to move in the other direction, towards the server. And so that's what probability really gets you in these systems, is it allows you to take observations from multiple independent places and you combine them to form the degree to which you believe something is true. So you no longer have sort of the hard, I believe or I do not believe in sort of propositional statement manner. And this is really why rule-based systems are things of the past and now we have probabilistic systems. So that's probability. The other element of decision theory is utility theory. So utility theory is this thing that was developed in economics. They're trying to put a number on how much do you value something? Sort of like, how much do you value this cup of coffee, right? And the answer is like, I don't know, like a lot, right? But they're like, that's not good enough. I want a number on that. So what did they do? Well, they played a game with you. They said, all right, I'm going to have you choose between this cup of coffee and the outcome of this lottery, where with probability P, you get the cup of coffee, and with probability 1 minus P, you get nothing. And we're going to start with P equals 0, meaning I'm going to ask you to choose between you get the cup of coffee, and with certainty you get nothing. And slowly I'm going to dial up P from 0 to 1. So you're choosing between getting the coffee with certainty and getting the coffee with probability P. And at some point, as P increases, you won't care, right? You'll be like, all right, getting the coffee with certainty is equivalently good to me as getting it with probability P. And that value of P becomes your utility, your value of having that cup of coffee. And interesting things happen, actually, when you have this formulation and you play this game with people. That if you try to do this with dollar amounts of money, so if I say, like, how much do you value $5, $50, $100, $1,000, you find that your utility tapers off as the dollar amount of money goes on, and that sort of describes a risk-averse profile, and it's sort of one of these great triumphs of economics theory. So the way that this works in intelligent systems is you reason about what is the utility of being in a state of the world. And the way you do this is you say, I'm going to start at that state, and I'm just going to take actions, and as I act, it will result in me ending up in new states, and at those new states, I will find things there that are useful. Maybe sometimes I'll find a $5 bill there, maybe in another one I'll find like a mugger there waiting for me, and that'll be really bad. And so the utility of being in a state is the sum of these rewards that you discover, discounted by some factor gamma. So these two things together give me what I'm interested in. They give me the ability to make decisions in the face of a totally uncertain world in which goals are only kind of vaguely specified. So I want to give a quick example of that. So drone navigation. This is an example I love because drones are cool. So let's suppose you have a drone in the bottom left-hand corner at the green circle. He's trying to get to the right circle, or the red circle, on the right. He's got two possible paths. The blue path, in which it's shorter, less battery will be expended traveling this path. However, it's fraught with turbulence. Anyone who's actually piloted drones, you know that more often than not you say, I want you to go forward, but what happens is it ends up on your neighbor's roof. And the reason is because wind is super strong, and these things are highly susceptible to wind. The alternative is the white path, which is longer. It'll take more battery in order to travel this path. But it's less turbulent, so that means you have greater certainty that you will reach there. So what should you do? How do I figure out, how do I reason about which path I should take at any given time? So to answer that, let's consider two possible extremes. So in one extreme, you have super low battery, but it's super important that you get to the goal immediately. So you don't have enough battery to make the entire white path. And so really it makes sense to just make a mad dash to the goal. That's a little typo there. On the other extreme, let's suppose that you have tons and tons of battery, you have all of the time in the world, and it's not super important to get to the goal, like whenever you get around to it. In this case, you can take the white path, makes sense. And so if you generalize this, you can see this idea that the uncertainty in the environment, in this case turbulence, plus the cost of being in this environment, in this case battery cost, and sort of the reward that's waiting for you at the end. If you reason about these three things, it should lead essentially to a policy of acting in this world. And the systematic, rigorous study of this problem is called Markov decision processes, which are super, super fascinating. These are things that I use at the office in order to, on my teams, in order to reason about how to build intelligent controllers in really big, uncertain, partially observable environments. And I wish I could go in greater detail, but we don't have time for that. I wanted to talk about another element of this in which you use agents to go out in the world to acquire data, called reinforcement learning, but I'm not sure that we have time for it, so I'm just going to skip past this section. So just a summary. AI is about acting in the world. It's about organizing a sequence of actions to achieve a long-term goal, and everything involved in that problem. Machine learning is a huge element of this, especially in modern intelligence systems, and they need each other in order to function. Now, why should you care? Other than that, it's really cool. The reason is because more stuff is becoming automated simply. So of course, there's this example of drones. I think everyone can see that drones are really transitioning out of the stage of just being for hobbyists, right? People are using them to do serious things. So the example in the upper left-hand corner is actually motivated by one of the things that we use it for at AT&T, in which people inspect these cell towers. Some of them are like 1,000 feet high in the air. People die every month doing this. And so the thought is, this is why robots exist. Let's have robots do this instead. And then in the bottom right is the idea of data centers, distributed file systems, infrastructure to support services is becoming more and more complex, impenetrably complex. And we need, to a greater degree, intelligent agents to reason about, to control, to influence, to diagnose what's going wrong with these systems. And these are just two examples that, at least that I think about in my day job. And as data scientists, all of you are uniquely poised to use all of your skills to build automation. And that's sort of all I had to say. And I'd be happy to take any questions that you have. Thank you very much.
You said a lot about stochastic control, but you haven't talked about the shape of that noise. In particular, have you done any work where that noise is shaped by, for instance, a deceptive adversary?
That is a good question. So we put uncertainty, right, in these probabilities, right? In which we say, I'm going to take this action, I don't know what the outcome of it will be, but I try to sort of hide that in these probabilities. Now, there's this question of, like, where did this uncertainty come from? It could be simply because there's just, like, noise built into sensors, and that's just sort of uncontrollable noise. But that uncertainty could also be directly from just other agents that are acting out of your control. And they're, like, maybe maliciously trying to prevent you from getting towards your goal. And this sort of gets into cooperative agents, and the other end, which is competitive agents. And absolutely, you can reason sort of directly about, like, I can think that the other guy is sort of going to do the absolute best possible move for him, sort of the most rational move, and then I can reason about what I'm going to do in response to that. That's sort of reasoning about pretending that your adversary is Kasparov. Of course, people aren't Kasparov, and so, except for Kasparov. And so a solution to that is what they call bounded rationality. They think about, there are these frameworks for thinking about an adversary is going to act, but, like, he's only so rational, maybe, like, due to skill or due to other factors. And then there are other frameworks, which gets into research that I did, which was applied at like LAX and the Coast Guard and things like that, in which you cannot observe your adversary. You have no idea who they are or where they are, but you know that they're just trying to exploit the predictability of whatever you're doing, and so you can think about ways to inject randomization into what you do, into the policy of action that you have. Yes, sir. I'm sorry, I cannot hear you. Could you repeat that, please? Yeah, so, well, the problem that injecting randomness is trying to solve is it's trying to minimize predictability. So it turns out that if you use a Markov decision process, that for many situations, the optimal policy that you get, that it cranks out, is a deterministic policy, meaning that for this state of the world, here is the one best thing you should do. And the thought is that if some adversary is observing you, that eventually they will exploit that. So one place in which that happens is, like, patrols, for example, right? Like, that's, like, the subject of every, like, bank heist movie, right? It's like, police come at precisely this time, and, like, we will use this time window in order to exploit that. And the idea is that you want to insert some randomization into there to sort of minimize the predictability, but not so much randomization that, like, you're not accomplishing anything in the first place. So that's sort of the problem that is meant to solve. And that sort of gets into anonymization. As some of you work on the problem of data anonymization, that sort of starts to get into that problem as well. Yes, sir?
Thank you for the talk, and I really like to say that AI is more about acting at the environment. How do you comment on the legal or ethical perspective when AI makes mistakes?
So the question is about the ethical question of AI making mistakes. So that's a good question. So there was a friend of mine, he wrote a book on robotics and sort of like the scariness of robots and the prospect of robots taking on more and more responsibility in this world. And he went and he interviewed this professor of robotics at CMU, and he's like, what would you do if the robot that you were presently working on lost control and came attacking you? And his response was, I would turn around and I would walk away very slowly. And the reason is because the robot, like, couldn't do anything. Like, it couldn't, like, it's just woefully incapable of doing anything remotely useful. So actually, I really like an interview with Andrew Ng. The reporter asked him this question, essentially the Frankenstein question, which was like, robots are clearly going to kill us. What should we do about that? And his answer was, listen, worrying about robots doing these things to us is very similar to worrying about overpopulation on Mars. Like, eventually, maybe, one day, we will have to seriously think about it, but that day is very far in the future. And people think reasonably about, some people think rigorously about this. For example, there's, in agents and multi-agents literature, they have what they call Asimovian agents, in which they think about this problem of, like, let's suppose there are a set of rules that you wish to enforce, that your agents either absolutely do or absolutely do not adhere to. And there are frameworks for sort of thinking about how to encode that, how to encode things like that. Another element of this is sort of building, not necessarily totally autonomous systems, but making systems that work with humans, so so-called human-in-the-loop systems, or what they call mixed initiative systems. So hopefully that's helpful. Any other questions? Yes, sir.
How does decision theory fit into non-trivial domains? Most of the strong AI has moved on. And I was interested in what your thoughts were. So, when you're applying it to logistical problems within the client-server kind of model you use, it makes sense because the branching factor is so big. But in non-trivial domains, the branching factor decision theory and decision theory overall seems like the main exciting factor in like what balance is there?
Yeah, so the question is, how do you use decision theory in realistic domains, simply because the branching factor of things is so high? So that's a good question. So you use the same business that you used in search, when I was describing search. Essentially, you use database methods to not do exhaustive search. You look at just the parts of the space that matter to your problem, is one of the big things that people do. And secondly, you think about how to distribute these problems. So today, computing power is so high that you can consider problems that are just like super large, that are like way larger than you could even 5 years ago. Yeah, and the way that you do that really is by, the way that people get traction in these is reason about the particular domain that you are working on. So the more that you're able to inject specific domain knowledge into these general frameworks, the more traction you're able to get in these systems in practice. One more question. Yes, sir?
Why are you interested in martial arts? And have you seen any overlap between AI and machine learning and
I've never been asked that question before. Nicely done. Okay, so why am I interested in martial arts? So I guess I've always been interested in like fitness, and Kung Fu is one of these things where like it requires like every physical skill, like endurance, flexibility, strength training. It's also very like community oriented. So you sort of are in this, you're in this studio with people, and you see them every single day, and you're working together, and you're sort of helping each other to become stronger and better, and to develop yourselves. And you sort of become, you really bond with people doing this. It's really cool to be part of this long, it's a sort of knowledge which you cannot pass in a textbook. Basically, someone has to demonstrate stuff to you, and it's sort of cool to be part of this thing where, like, for hundreds of years, like, teachers have been saying, here's how you do X to students, and sort of being part of this chain is cool. How does it relate to AI? I guess in fighting games? So, like, I understand that Virtua Fighter has a very elaborate AI system. I heard that it uses decision trees. Thank you very much, everyone.